Again, welcome to our presentation detecting issues with in-band telemetry in OSM-Orchestrated core networks, which we present here from the network lab at the SimulaMet Metropolitan Center for Digital Engineering, SimulaMet in Oslo, together with my colleagues Azza here from Oslo and Mah-Rukh from the University of Gloucestershire in England. In the United Kingdom. Well, first I would like to give you a short motivation of our work, which is in telemetry, of course. And then I would like to show a short overview of the testbed setup we made for applying in telemetry. And of course, provide you a few details about how we orchestrate this testbed network using open source MANO. And then, of course, we come to the main part of this presentation and short demo today, which is in-band telemetry using P4 protocol, programming protocol independent packet processors, which is involved, of course, by the live demo. But first, what's the motivation of our work? Well, we would like to do research on 4G and 5G networks. Obviously, we therefore need testbed setups. And for this, of course, we use open source MANO to orchestrate these setups, particularly generate such setups with certain parameters, manage them, and finally remove them when the test is over. So obviously it is then useful to obtain performance metrics about the components of such setups, which is in a basic way possible already in OSM. For example, it's possible to collect basic metrics either via Juju or via the NFVI features and get things like, for example, packet counters or CPU utilization or memory utilization of VDUs. So this is fine for having an overview over the components of the network, but of course it will not provide any user-related quality of experience. So you do not get the perspective of the actual user of a mobile network. The user, of course, sits with his mobile phone and uses the mobile network. And of course the question is the user experiencing a good service of the network or not? So we need more fine-granular telemetry, and the idea is, of course, then to use in-band telemetry, that is, use information inside the packets to get telemetry information. And for this, of course, we need features to add statistics information to packets, to process this information added to packets, and of course, finally, to remove this statistics information again when the packet leaves the network. And the idea is to use programming protocol independent packet processors, P4, which is a standard for programming network devices, particularly switches. It is, instead of having actually only the switching functionality, it's possible to fully program the switch. And P4 is a standard, so in the future you can then probably just buy any off-the-shelf P4 switch and apply your own programming to this switch. It is your own programming for processing and handling packets. So it's very flexible. And of course, we want to use this for in-band telemetry. This is our idea. And for this, we have, of course, made our setup based on OpenAirInterface. OpenAirInterface, probably I do not have to explain much here, since at the OSM Ecosystem this has also been used for 5G setups. So it is in fact just the software implementation of the core network part, as well as the eNodeB part of a mobile network, particularly is open source. So quite interesting for using this for research. What we do in our setup is, of course, we are instantiating core network, VPC and packet core for 4G network consisting of MME, HSS, SPHWC, and SPHWU. And of course, we do this as VNFs, instantiate everything as network service in open source MANO. And open source MANO is using sham-based configuration for our components. So far, so simple. But of course, we want to do invent telemetry as before. So therefore, we add software switches in the S1C, S1U, and S3I interface. Also, not shown here, but we have also implementation of a FlexRun in our setup, but this is not relevant here for this demo today. For this, we have now the Judo containers doing the management and collecting basic telemetry information. But for invent telemetry, we have our P4 switches. As I've said, these are software switches, so obviously then we have implemented them as VNFs as well, and then realized everything as network service. And these software switches, P4 software switches, run then custom programming for adding telemetry and providing this telemetry information to a component called telemetry collector. So far our setup, and now my colleague Mah-Rukh is going to explain you some more details about before and the invent telemetry itself.
Okay, so here we are adding like telemetry information that we are tracking for the incoming packets on the S1U interface, and these are added to the IPv4 option header. This header is then added to the incoming packets, but the incoming packets actually have two versions. The first version is untempered, and it is sent to the destination by the P4 switch as it is. And the other version is the mirror, is the cloned one. In that cloned one, we add the telemetry information, and this packet there is then mirrored towards the telemetry collector. So actually there are two versions of the packet, one that is not tempered and the other one in which the invent telemetry data is put. So once this data is put into the packet, so these two versions of the packets are then emitted by the deparser of the P4 switch, and the mirror packet actually arrives at the telemetry collector. This telemetry collector has already been shown by Thomas in our setup. So the telemetry collector actually extracts the telemetry information from the incoming packets and logs them for future use for further analysis. So there is a small demo in which I will be showing the P4 program that we have developed, this P4 program that I have just explained. So this is at the S1U switch, PM, and which we have made into a P4 switch through BMB2 version of the switch. And here you can see that at the very start, we are defining the headers that we want to add. For example, the IPv4 option header that we will be adding to the telemetry, to the mirrored packet. So we are defining what types of field will this IPv4 option header will have, and what data we will include it in it. You can also see like the length of each of the fields that we will be putting as a telemetry information. Once you define this type of header, what we do, we can either in the ingress or the egress of the P4 program add the telemetry. So we are doing we are adding the telemetry data to the outgoing packet in the egress. Like here is the code in which we specify the modification that we will be doing to our packets. And finally, this mirrored packet and also the original packet will be transmitted out from the P4 switch through the deparser. So I was only showing this demo to state like how the P4 programming can be has the potential to find out any performance issue in the end-to-end communication. And my colleague Azza will be showing through an example the ability of this P4 program. Thank you.
Hello, everyone. I am Azza. I'm going to present our investigations of P4 telemetry in detecting any performance degradation in the network. In this analysis, we conduct two different experiments. The first one, which represent our baseline, running the network under normal behavior. We run TCP, iPerf downlink from a test server to the UE, and then we collect end-to-end performance measurements at the UE side. For example, we are collecting RTT, jitter, and the bit rate and packet loss. And also we are collecting the B4 measurement through the telemetry collector. In the second experiment, which represent the performance degradation, we introduce bottleneck at S1U by running TCP iPerf from the SPGWU to the E node B, while keeping running the iPerf between the test server and the UE. We collect the same measurement as before, and then we formulate our problem of bottleneck detection as anomaly detection, using the measurements from the UE and the B4 as our features. We leverage a deep learning model autoencoders to detect the bottleneck. We train our model using normal data, which is our baseline experiment, and then we test it using a combination between the normal data and the bottleneck data. Here we are showing our findings. We compare our model performance when using only UE measurements and when we are using UA measurements and the B4 measurements as well. So we can see that the overall performance of the model increased by 12% in terms of F1 score. And interestingly, the recall increased by 14%, which is a good indication that the B4 telemetry helps in increasing the number of the bottleneck that detected correctly by the model. Finally, I'm going to show a live demo from one of our experiments. Here we have our server running, and then at the UE side, we have a real phone. We just mirroring it in the PC through screen copy, and then we run the iPerf at the UE, and here we can see that the packages are going, and then we are running our telemetry collectors. The telemetry collector here to show the packets, and yeah, here we can see, and here is our real phone. We're connecting to the PC. That's all from our side. Thanks for attention, and if you have any question, please ask.